This is something which hatched over spring break. It's the tree-forest ratio. It's a classical topic in graph theory to study spanning trees, to study spanning forests. And here are the definitions. So we take a finite simple graph, like this one, like the house graph, and then we can look at the Kierkov matrix. By the way, here I have everything with the example of this house graph. So the Kierkov matrix, which is the divergence of the gradient, which is zero-dimensional Laplacian, which can be written as the diagonal matrix with the vertex degrees minus the adjacency matrix. So that's something which Kierkov has done 170 years ago. And the pseudo-determinant of this matrix, the product of the non-zero eigenvalues, the eigenvalues are always non-negative, and there's one zero eigenvalue if it's connected. And we have the pseudo-determinant is the product of the non-zero eigenvalues, which is the number of rooted spanning trees. This is the Kierkov matrix theorem, and the number of rooted spanning forests, Chebotarev-Shami's theorem, spanning forest theorem, which is that's a Fredholm determinant, also very natural notion in linear algebra. Here we could take the determinant because the eigenvalues of 1 plus k are always bigger or equal to 1. These are integers. And then we can look at as I started to look at this 1 year ago when I looked at the graph complements of cyclic graphs, which is a very interesting topic. What happens is here with this ratio. So this ratio had actually here a limit, which made me excited. But so what it is, it's just you write down this determinant of 1 plus k over the determinant of k. And then what you have is its product of the non-zero eigenvalue 1 plus 1 over lambda. Very natural spectral notion, only depending on the spectrum of the Kierkov matrix. So I call this the tree-forest ratio. And just by the way, the trees and forests, these are one-dimensional features of a graph. And it's important because it allows you to organize a graph. Trees are important in computers. Trees, directory trees, etc. So they're a way to organize things. It's very important also in physics. Trees, and you wonder about the number of trees, and there's no surprise that here only the zero-dimensional Laplacian comes in. So last winter I looked at the torsion, which involves all so this is the zero-dimensional Laplacian here. So this is L0. So in general, you can also look at higher order trees, and so that's also interesting. And there might be also tree-forest ratios there. I did not study that. I just looked at this case of kind of a one-dimensional classical situation. So that's Chebotarev-Shami's, that's Kierkov. And I got to this myself by looking at Cauchy-Binet in linear algebra. So this all can be seen just directly from a Cauchy-Binet formula. So that's a tree-forest ratio. And then what is also kind of interesting then, it turns out this explodes pretty fast. For example, if you do barycentric refinements, so this is a graph, you look at the barycentric refinement, and so you take the complete subgraphs as vertices and you connect two if one is contained in the other. It gives you the barycentric refinement. You can iterate that. And I got some universality about the spectrum about 6 years ago. But here I look, of course, you can also look at other quantities, how they behave. And in this case, it explodes pretty fast. This number of trees, number of forests, they are growing very, very fast. And it turns out that the volume, the number of maximal complete subgraphs plays a role here. So in this case, we have one maximal of a triangle, and so the f vector encodes this. So in this case, the f vector is 5, 6, 1, 5 vertices, 6 edges, and one two-dimensional simplex, which is a triangle. Then you can compute Euler characteristic, you can compute Laplacian, this Hodge Laplacian. You can compute especially the zero-dimensional Laplacian, which is the Kierkov Laplacian, something 170 years old. And so you can look at the determinants. You can compute this. And then what I define then is just this tree-forest index. So the logarithm is something natural to take because this grows exponentially, and then you divide by the volume. And that has then a chance to converge. And indeed, I prove here that this converges when you take barycentric, always when you take barycentric refinements. Also interesting in the context of spectral theory is always the zeta function. When you take any Laplacian, you can look at the Hodge Laplacian, you can look at the Dirac operator. Actually, you usually take positive. You take positive eigenvalues here because you don't want to have here an ambiguity with defining the zeta function. For example, for the circle, you can do that also for manifold. For the circle, you get the Riemann zeta function. So that's a very natural notion, the spectral zeta function. So in this case, you compute the eigenvalues of the Kierkov matrix, and then you just write down the 1 over lambda 1 to the s, 1 over lambda 2 to the s, 1 over lambda 3 to the s, 1 over lambda 4 to the s, and the fifth one you leave away because that's the zero eigenvalue, which is always present. And so in this case we have here 55 spanning trees, rooted spanning trees. So it's important. Rooted means also you have a root, like a directory in a computer. You fix one of the 5 points. If you divide by 5 here, so there are 11 trees here, spanning trees, and then you can also look here at the. So this is the number of rooted spanning forests. And then you can look at the ratio and take the logarithm, and in this case there is just one maximal simplex. So that's actually in this case the index. That's the index of this graph, 1.337. Then you can play around. It's actually tough to compute for barycentric refinements here. This grows pretty fast, but you can see that it converges. Two-dimensional case, you can also see in the one-dimensional case that it converges, and indeed that's one of the things I found that it converges, and it's not so difficult to prove. It's actually, I can explain it quickly. But that was the first result was when you take these small graphs, graph complements of cyclic graphs. Graph complements of cyclic graph, they're homotopic to spheres or wedge sums of spheres. It's very interesting, higher dimensions, so they grow. The dimension grows, and so they're very small graphs and high symmetry, and a very nice topic. I looked at especially at the curvature there. There's some universality of curvature, and so it's a very interesting topic. These are graph complements here, the graph complement. So this is surprising, right? Usually the number of forests grows much faster than the number of trees. The main result is that under barycentric refinement, you take any graph, you take the barycentric refinement, and you compute this index. The index converges to a number which depends only on the dimension, the maximal dimension. So in the case of d is equal to 1, d is equal to 1 is special because we can, for example, take cyclic graphs. If it's universal, we can just take cyclic graphs where we have all the eigenvalues, and we can compute the number of trees. The number of spanning trees is n squared. The number of spanning forests is the Lucas numbers. So there are some recursive things that are exploding exponentially. And then if you take if you take the logarithm, only the exponential growth matters. And so that's why you have then the Lucas numbers grow like golden ratio to the power n, and so 2n. So you have that result that the golden ratio here really appears here in the constant. This is the one case I can compute this constant. In general, I cannot compute the constant yet. Just even approximating is hard, but I know it exists. Also interesting is just if you make an expansion of that you know, you take the logarithm of this, you write this, and then you make the log of 1 plus 1 over lambda, you make the Taylor expansion there, then you get you can express it using the zeta function. So this is a zeta function here. So this is a function which is entire, right? So this is e to the s times log of something positive. These are entire functions. And so this is kind of important. So this is an entire function. And I studied this in the case of cyclic graphs. What happens in the limit? And I studied it also in the case of the connection graph, where it's kind of more natural and easier to compute where there's a functional equation. So in this case, the roots are there's no functional equation, and but you can still look at that, and then you can look at the zeta function at 1, 2, 3, 4, and you take the alternating sum divided by s. So that's the expression of the logarithm of tau. So you can compute this now. Once you have this expression with the zeta function, you can define this tree forest ratio also for manifolds. You know, in manifold, if you look at the manifold, Riemannian manifold, there is no, you cannot look at the number of trees and number of forests there. That doesn't make sense. It's just, you know, uncountably many, and it's not even clear what you actually call trees and forests. So, but you can look at the zeta function. So you have the in the case of the circle, where it's the Riemann zeta function, then you can actually compute here. So in this case, it's the sinh of pi over pi, which is a beautiful number. Too, in this case, you can compute this the log of tau. So this is what I wanted to say. And just that it doesn't get lost in my hard drive, because I will forget about it and do some other things. Cool. That's it.